Okay, welcome everybody, thank you. I'll put a quick plug in for the FEMM Hub training session. So this is taken from a 3-hour training session around last year on SMC, and it's going to be running again in, I think, November. Hopefully I've condensed it down to 20 minutes, but I'm ready for the chair to rugby tackle me off the stage when we get to 40 minutes. So I'm going to talk about electrical machines in the third dimension. Using soft magnetic composite material. So there's lots of contributors to this presentation, PhD students, past and present, research associates, past, present, and many colleagues at Höganäs AB in Sweden. So I've pinched lots of pictures and bits of data and stats here. A little bit of it is mine. So to start off with, so electrical machines traditionally have been made from laminations. We've taken them, we've stacked them, and effectively you're getting an extruded two-dimensional shape. So the question here is, can more be gained from using the third dimension? So a traditional stator, we would take the laminations, stack them up, wind them. Similar process for the rotor. In there we would be inserting the permanent magnets. So the question, what we're looking at today is we'll consider making the machine from a powder, from soft magnetic composite. So first question is, why don't we just take pure iron powder, compress it, wind it, and use that as our electrical machine? Well, we've got rotating magnetic fields in there. Compressed pure iron would be highly conductive. We would have huge eddy currents in our machine. It would become, I think, less of a motor and more of an induction heater. So we need insulation. The laminations do the job of that. We've got the insulation between the layers. With soft magnetic composite, we've got to have the insulation on each of the particles of iron powder. So soft magnetic composite is it's high purity iron powder, made using a water atomization process, and it's 100 micrometers or smaller, depending on the grade of the powder. It's deformable, so when we squash it, it does change shape and it does interlock itself. And there's various surface coatings on there. First off, to ensure each grain is insulated from the one next to it, so there's electrical insulation. But also, so there's lubricants mixed in there, so when we compress the powder, we get the shape we're aiming for, and it holds together afterwards. So the powder, it's sold literally in a tin, a little bit bigger than a paint tin. It's sold as a ready mixed powder, so the iron is insulated and the lubrication mix is mixed in there in the right quantity and distributed in the correct method. The soft magnetic composite itself, making the powder and pressing it is a bit of an art form, so there's a balance between getting the purity of the iron right, the distribution of the powder particles, all of that affects permeability, it affects coercivity, the particle size affects eddy current losses, so when we look at different grades of soft magnetic composite with different loss or different mechanical properties, it's quite often the particle size that is the differentiator there. The coating on the powder, that has an effect on the eddy current losses. So in an ideal world, the particles would be hexagonal, we would squash it all together and you would have that, for those of you who get the cultural reference, this Blockbusters board over here. But of course real life isn't that nice. The particles are quite irregular, they've got spikes and lumps and bumps. When we squash it together, those lumps and bumps come into contact, they do break through the insulation. So we don't get perfect electrical insulation. There is a bulk resistivity, so we can have a component, and I've got some on the table over there. You can measure an electrical resistivity. The trick is to make that as low as possible. So a little bit on compaction and heat treatment. So this is a axial flux machine being made. And hopefully this video works, yes. So there's the powder poured in, there's the press doing the squashing, and there's the component coming off the bag. So about one component every 4 or 5 seconds, thereabouts. When they come off the press, they're in what we call the green state. They're not mechanically strong. They've got the kind of consistency of a ginger nut biscuit. You can break those bits off. This is just a little bit of measurement to check the size of them. So once they come off, they're then heat treated. So it's not sintering. That's the point. The temperature is between 550 and 650 degrees, depending on the properties you want. That relaxes the stresses in the material. It helps the thing hold together, and it comes out with a much greater mechanical strength than the initially green state pressed components. So these components, they're pressed in a press of varying pressures depending on what we're doing. As a guide, we would want to press the component between 600 and 800 megapascals. So the size of the component and the size of the press is very important. So typically 600 megapascals, so the lower press pressure, a small 100-ton press, we would be able to compress a component that's about 40 by 40, so I guess a cube about that sort of size. If we're wanting to compress something with a reasonable diameter, so say 200 millimeters, we're going to need a 2,000-ton press. And the problem is they're a little bit few and far between. So you see the 70-ton press on the left there. The person on the ladder is literally pouring SMC from the metal tin into there. On the right is a 2,000-ton press, and you can imagine the operator being quite small compared to that. So there are few of those around. So there's a balance between component size, pressure, and actually what's available to press the stuff. So a little bit on the design of the electrical machine using soft magnetic composites. So the powder, it has a lower magnetic permeability than solid iron. It has higher loss at low frequency. The hysteresis factor is much higher. So at low speed, low frequency, the iron loss is dominated by hysteresis. The eddy current loss is very low, and what we find is at the higher frequencies, the hysteresis isn't rising as fast as the eddy currents, and we have lower loss at high frequencies, so there's a balance to be had in there. So we find that if we were to take an electrical machine and redesign it using SMC, a direct replacement of that machine would be worse. It would have lower permeability, it may have higher losses, it may not be as good. So if redesigning using soft magnetic composite, we need to use all 3 dimensions and radically redesign the machine and rethink it to get the various advantages that are possible from using the material. So we've got full 3-dimensional freedom in design. So we can have shaped teeth. We can curve the tooth tips. That means we can have a much tighter winding, better thermal interfaces between the coil and the tooth itself. You'll see one of those over there a little bit later. We can design features into it and move to a more modular design, so components start to interlock. The tolerance between them is very high. We get decent precision there. We can embed things like sensors, locations for coils to come in and out, heat pipes, and so forth. And we can use new 3-dimensional magnetic topologies or electrical machine topologies, which would be not impossible, but certainly more difficult to do using laminations. You saw on the video, this was the axial flux machine, a single-sided axial flux machine, and that's one of the components there. One other benefit which has always been around but is becoming more of interest is the use of the material in the circular economy. If you take a laminated machine and want to recycle it, you've got to remove the copper completely, otherwise it pollutes the steel when that's recycled. You get copper in there, it's useless. So it's quite difficult to get the copper off. You've got to manually cut it, attack it with an angle grinder or whatever. The soft magnetic composite, it is a fairly brittle material. So if you took the machine and squashed it, the iron powder would separate away and you would be left with the copper. So there are potential benefits there. It's easier to break. So a bit on three-dimensional electrical machine design. So if we're going to use, if we're going to curve the tooth tips or use a new topology, we would have to design using three-dimensional finite element methods. That is trickier. The software costs more. The expertise of the person using it needs to be higher. There are various tips and tricks and wheezes that we have to use to be able to get reliable results out. It also takes time to solve. So I've got a personal record of 14 days on one of these. I think with a newer computer I might get that down to 7. But it needs thinking about. So we need to think about where we can reduce the complexity of the simulation using magnetic periodicity, axial symmetry, and so on. When we compare simulation versus measurement, it's not bad actually. The back EMF simulated versus measured is usually within 5%. We've got some measured and simulated results there. The static torque can be a little bit more dependent on what type of software we're using. And with Hergeness, we've done all sorts of studies of various packages versus one another, and it tends to be the cogging torque, the zero-load cogging torque is where there is the largest difference. So there's a little bit of experience and understanding needed there. We've done quite a lot of work on iron loss. So Dan Gumbleton would have, former PhD student, he's tested numerous laminated rings versus different grades of soft magnetic composite and measured the iron loss of those. And there's a brief summary there of the difference between the simulated result and the measured result. And you'll notice for the thicker laminations, so the thinner laminations, the difference between what the manufacturers tell us the iron loss is and what we're actually measuring is something like 27%. So we're measuring more iron loss than we're expecting. For the thicker laminations, that gets worse. So we're at up to 45%, or for the 0.5 lamination, we're almost heading towards double the measured loss compared to what we're expecting. For SMC, it's a much tighter bound. So we're kind of within plus minus 4% measured loss versus simulated loss. So I've given this part of this talk to an international audience and confused them greatly with from the UK. But the soft magnetic composite, it does do what it says on the tin. There are fewer nasty surprises when we get to building something. So let me give a few application examples before I finish. So we've done lots of work with transverse flux machines or modular pole machines. These are really good machines for high torque, low speed, so direct drive. We've applied these to in-wheel motors for electric bikes and scooters. So the state of these machines is nice. It's made up of single component pressed stator pieces and nice hoop coils which sandwich together and stack up. So that's quite nice, but the rotor on them is awful. So the example I've got on the table over there is an 80 pole rotor. So that's got 80 SMC pole pieces and 80 magnets. And it's assembled magnetized, so we've got SMC magnet, and the whole lot's trying to collapse in on itself. And I think some thought around how that could be improved. Co-compaction, the use of two powders, squashing would be nice, and I would love to talk to anyone about that and show you some bits over on the table over there. So that's been used for electric bikes. There are other low-speed, high-torque applications we've been involved in looking at. But yeah, as I said, the manufacturing challenge there is that rotor, how to make that thing much more easily. I think that's the main part that holds this piece back. Single-sided axial flux machine, you saw that being made. That's a nice simple construction. So the stator is a one-press component, heat treated. The coils can be produced off the machine, so a nice precision, nice tight winding, and then they're just slipped over the teeth. And then you've got the rotor, permanent magnet rotor. That's the bluey-green bit on the right there. We've done various studies looking at different axial flux machine topologies. So the single-sided version you see there, we've looked at the YASA. So the YASA is the yokeless segmented armature. I missed a letter somewhere. So you've got the stator in the middle and it's got two rotors on either side. The challenge there is getting the heat out of the middle. You've got the rotor on the outside, and the stator on the inside, and the stator is held in place by non-magnetic components, so there's a lot of thermal insulation and cooling issues there. We've also looked at the torus version of that, where the coils are effectively turned by 90 degrees. When we look at the various stats there, so torque per magnet kilogram, torque per active mass, cost, and so on and so forth, the YASA topology does come out really rather well. You see the red numbers there are the maximum or the target. The single-sided axial flux machine comes out quite nicely on torque per volume, and it's quite a simple structure. We've looked at radial flux machines with rounded tooth tips. So that enables us to have a nice tight coil. That coil could be produced elsewhere separately to the tooth and then placed over the tooth, or it would be possible to have a bobbin winding process where the coil is wound directly onto the tooth with suitable insulation in between. On the example here, this is a compressor motor. We did, by having that shaped end winding, we were able to shrink the axial length of the machine, shrink the total length of the conductor, and thereby the resistance and the winding loss. Recent work we've done is on higher speed machines, so running up to 100,000 RPM. That's using the newer grades of soft magnetic composites. So we're finding that the losses in this material at these high frequencies is lower than a reasonable lamination, certainly not some of the really exotic Japanese laminations that we may get, but this is looking quite good, and quite nice in terms of losses. So to conclude, perfect, I've got the 2-minute sign there. So soft magnetic composite, the components are magnetically, thermally and electrically isotropic, so the properties are the same in all 3 dimensions. To produce a SMC machine, we need to design it using 3D design tools. That requires skill, software, time and cost. But it gives us design freedom, so we're able to incorporate different features, use different machine topologies, do different things with the material. And the way the material is developing, the ion losses, particularly at the higher frequencies, are looking promising. We're getting a crossover point whereby the losses in SMC is lower, above 400, 500 hertz, compared to a reasonable lamination that would be used for that application. So that's me. Thank you very much. We may have time for a question or two.
Okay, we have a couple of minutes.